Hello and welcome back to AP Physics. We're in a new unit, so we're starting a unit on forces, and that's what we're going to be doing today. If an object is stationary and you want to get it moving, you'll have to apply a force. A net force changes the motion of an object. So when we push on the truck and it moves and starts to pick up speed, because it's changed its velocity, we say that it has accelerated. So forces cause things to accelerate. What is a force? A force is simply a push or pull on something by something. Forces are going on constantly all around you. Would a push or pull have a direction? When I pull something in a certain direction? Sure, I would. Okay, since forces have a direction, we say that they are vectors. So we'll be applying some of the stuff we learned last unit with forces. So forces have a direction. We can talk about it as left, right, up, down, north, south, east, west, or positive and negative, which we'll certainly do that. So if we want to accelerate an object, there's three ways that we can cause it to accelerate, cause its velocity to change. We can cause it to speed up, we can cause it to slow down, and we can cause it to change direction. And it's the direction of the force compared to the direction of motion that causes which one to occur. So if I push an object the way it's moving, it speeds up. Sure. Okay. If I want to slow an object, I got to push opposite the way it's moving. Okay. And if I want to get an object to turn, I have to push it from the side or perpendicular to the way it's moving. So this is an overhead view of a tractor trailer here. So it's driving down the highway. It needs to make a exit and get off on the ramp here. So there's going to need to be a sideways force. So there has to be friction between the road and the tires that give it that perpendicular force that causes it to change direction. Now, if we apply more than one force on an object, let's say we've got two people pushing equally hard on the truck, it's not going to go anywhere. These forces cancel because they are equal in magnitude and opposite in direction. So that truck will not go anywhere if it wasn't moving. Okay. So now if we were to say that each person was pushing with a force of 5 newtons, which wouldn't be that much of a force, and we were to add these force vectors together, let's say we had a force vector of 5 to the right and then 5 to the left, and we were to add these force vectors together, from last unit we know that we'd get 0 because the 5 to the left would actually be negative. So when we talk about the net force, what we're doing is we're really adding up the forces, and we're determining the net force acting on an object, the sum of the forces, so the vector sum. If an object has forces on it that cancel or add to 0, these forces are said to be balanced forces. They do not affect the motion of an object. So if an object is stationary, it will remain stationary, and if an object is moving, it will continue to move in a straight line at that velocity until something else changes. Now, if the forces are not equal in magnitude, then you have what left over, a net force. So if we have 5 to the right and 3 to the left, we'd have a net force of 2 to the right. So that would be the sum of our forces. If we give a book a shove and we let it go, it's going to slow down. And we know what causes it to slow down will, of course, be what? Be friction. And Galileo, and this is kind of in him laying the foundation for Newton's laws, Galileo experimented with things that didn't have a whole lot of friction, such as balls that were rolling along the ground. And he found that they slowed down very, very little if it was on a very smooth surface. He basically came to the conclusion that if there was no friction, then the balls would just keep rolling forever and ever and never even stop or slow down. So he's really laying the foundation for Newton's first law here. So this is contrary to what everyone thought. Everyone thought that an object naturally wants to stay still, and naturally wants to come to rest, and things tend to do that. But that's just because friction is constantly around. Except for the heavens. The heavens had their own laws of physics. The planets could keep moving because they weren't on the Earth. The laws of the Earth physics didn't apply in space. So anyway, along comes Sir Isaac Newton, and he studied how things move as well, and put a lot of his ideas down in a book called Principia when he was 24. Basically, we're learning Newtonian physics this year. What comes after would be relativistic physics, quantum physics, which you'll get into if you take college physics. So Newton's first law basically says it has balanced forces on it, it's going to keep doing what it's doing. Okay, and there's any number of ways I can rewrite that. One way I can say it is an object will keep moving with a constant velocity, the same velocity, unless an unbalanced force causes it to do something differently. Or I can use math and define Newton's first law and say the change in velocity is zero if the forces add up to zero. So if the forces cancel, then the velocity doesn't change, is all that means. Normally I would do a little demonstration with a hovering disc that floats on a cushion of air, and once I give it a push, it scoots along the classroom floor and slows down very, very little, which is a good example of what happens. You can see Newton's first law when you get rid of friction. Okay, so balanced and unbalanced forces. So if we were to look at these two forces here, would they be balanced or unbalanced? They would be balanced. What if we tilt the forces to the right? Would these be balanced or unbalanced? Balanced, okay, because they're equal and opposite. Okay, what about these forces? Unbalanced. They're opposite in direction, but they're not equal in magnitude. What about this? We shrink the other force. That looks pretty balanced to me. And the final one, we've got an up and to the right. Will those forces cancel? No, they are equal, but they are not opposite in direction. They have to be opposite in order to cancel. If I wanted to find the net force and I had two vectors that were perpendicular to each other, how do you add these vectors? You make a triangle and you use Pythagorean's theorem and sine, cosine, tangent, and that's what you would do to find the net force. Just like last unit, make the triangle, use sine, cosine, and tangent. So the property of matter that we say imbues it with this tendency to keep doing whatever it was doing is inertia. You can think of it as the laziness of matter. Okay, if something is stationary, it wants to stay stationary. If something is moving, it wants to keep moving. It doesn't want to change what it's doing. Newton's first law is often called the law of inertia, because it basically says what inertia does. You guys have probably seen the tablecloth trick before, where you yank the tablecloth and all the place settings stay put. This is a classic example of inertia. The place settings are stationary, so when the tablecloth is yanked very quickly, the table settings pretty much stay put where they were at. Pretty much because, well, there is a little bit of an unbalanced force of friction between the tablecloth and the settings. But for the most part, it does stay put because by doing it quickly, you minimize that friction. This is a great picture. So what I want to draw your attention to is the prize fighter's lips. It looks like someone is pulling them to the right. Okay, but that's not what's going on. His head is being accelerated to the left quite rapidly, and his lips are trying to stay put. So it looks like something is pushing his lips to the right, but it's really because something is pushing his head to the left. Whoops, okay, I'm guessing that did it. So whiplash, I'm sure you've heard of whiplash. One way you can get it is cars didn't used to have headrests. And if you'd be sitting at a stoplight or whatever, minding your own business, stationary in your car, and if someone were not to pay attention and then crash into you, what would happen is your head would whip back. Now, having said that, that's kind of a lie. Your head doesn't really whip back. Your head tries to stay put while the whole body of yours is accelerated forward. So your head is left behind, but it's not actually thrown back from where it was. It's trying to stay put. Let's see if, let's pull this up. So this is what happens when you, oh, it's probably not gonna, no, this should record. So this is what happens when you're not wearing your seatbelt. And what I want you to notice is that the person, when the car hits, the person continues to travel at the same speed as they were moving before the car begins to slow down. The car is slowing down, but the person is not. The person's inertia keeps them traveling at a constant velocity until something does exert an unbalanced force, like the steering wheel on the windshield on the face. But yeah, look, the person just keeps moving at the same speed. So if you're going 60 miles an hour and you hit a tree, you're going to hit your windshield at 60 miles per hour. And of course, we'd like to not have that happen. So there are safety measures that slow you down a little more gradually and safer locations. You can see his face imprint that they color the face to see where it lands. Okay, so anyway, that's a good video clip. So this is a picture of, I don't know if this picture is real or not, but it's kind of cool nonetheless. If it's faked, it's a good fake. So this truck stopped, but this big rock that it had in it kept moving because the rock has got inertia and the truck slowed down. Okay, so when you throw a ball, okay, what keeps it in motion after it's thrown, after your hand leaves it and is no longer pushing it, is its inertia. Is inertia a force? No, inertia is not a force. You're never going to put inertia on your force diagrams when we start doing those. A tennis ball has inertia, and if you play tennis with a tennis ball, you can easily change the motion of that object. Even though it's got inertia, you can change the motion of its object and reverse its direction of travel. Now, if you try to play tennis with an 18-wheeler, the 18-wheeler also has inertia, but you're not going to be able to get that 18-wheeler to bounce back. Why did the 18-wheeler have more inertia? The answer is because it's got mass. And the more mass an object has, the more inertia it has. But inertia is not a force. It's the resistance to changing speed to a force. Okay, and that is where we're going to stop for today.